Hello everyone, welcoming you to this session to discuss the concept of inter-process communication and synchronization. So in the previous sessions, we have discussed how these processes are going to be interconnected with each other, and now we will discuss about how communication is going to happen among these processes and how the control information is going to be exchanged. And to start with, we should be aware of this cooperating processes always have to execute their work in a synchronized fashion. So what we mean by synchronized fashion is if one processor is using the resource, obviously the other process should give away. If more than one makes an attempt to share the same resource, it may end up in a conflict. So in such cases, how we are going to synchronize the activities of the cooperating process. So that is going to be discussed in detail about this inter-process synchronization. And usually we will try to enforce the correct sequence of processes. Only then the mutually exclusive access can be made to access the shared information. So multiple in a multiple process system, more than one process will make an attempt to make use of the memory, and if it is going to be for read operation, we can allow all the process to read. It's not going to create any issue. But in case if it is going to be a write request, then if I allow more than one processor to share the same memory, obviously it will end up in a conflict. So to resolve that, we have to go for a synchronization mechanism that will decide who is going to use the resource and for how long it is going to use the resource. So in all the multi-process systems we have discussed so far, we have so many such mechanisms available to synchronize this activity. So we have the low level primitives which are implemented in the hardware. So anything which is implemented in the hardware is going to be more efficient in terms of speed, but of course there will be some lack in flexibility. And there are some primitives which are available which can enforce mutual exclusion by means of some complex mechanisms implemented at the software level. So what we mean by mutual exclusion, more than one attempting to share the resource and only one will be allowed, obviously the others will be controlled not to enter into that common space. And there are other mechanisms like binary semaphores which are also available to enforce this mutual exclusion policy. Now we will just see how this mutual exclusion is going to happen. So before that, we will just refresh some of the key terms related to this inter-process communication and synchronization. So the first property which we always expect is that we have to provide an orderly access to the shared memory. So if resources are going to be shared by many processes, who is going to use and for how long they are going to use, this sequence order has to be determined. The mutual exclusion will take care of that, and also it will take care of protecting the data from being exchanged simultaneously across the processor. And one more important topic which we have to be clear is that the critical section. So what actually we mean by critical section? It is a program sequence that must complete execution before another process access the same shared resource. So if more than one process wants to use a particular portion of a program, it has to be done in an exclusive manner. So only one should be allowed to enter. And after this particular process completed its activity, if it is leaving that resource, only then the other processor should be allowed to enter into that portion. Any portion which is going to critically affect the result, if we allow multiple process, is going to be identified as critical section. So, who is going to enter into that and how we are going to ensure mutual exclusion is going to be provided by some mechanisms available for it. And one such mechanism is called a semaphore. So, semaphore is nothing but a binary variable, and that binary variable will act like a lock. So suppose for example I have only one resource with me and more than one is competing for that resource. So somehow or other I, based on some priority or some scheduling manner, I decide okay this process can start using this resource. And once a processor is starting using started to use a resource, it has to lock the resource. Only if it is locked, it can prevent other process from entering into that resource. So that lock is nothing but a semaphore, which is a binary variable. It is not a hardware, it is a binary variable. So whenever a processor makes an attempt to enter into a resource, it will immediately set the binary variable to indicate that that resource is with its control. All the remaining competing processes has to wait till the lock is released. So that is going to be implemented by the concept of semaphore, and it is called as a binary semaphore because if it is 1 it means it use, if it is 0 means it is free. So whether it is locked or it is released, so that is going to be indicated by the binary state. and the testing and setting of the semaphore itself is going to be a critical operation, because more than one processor is going to check whether the lock is locked. Okay, so in that case, the testing operation also has to be done in a single indivisible operation. What we mean by single indivisible operation, it is a kind of an atomic operation. Atomic operation means it has to be done till the end. So in between, nobody should interrupt. So when a processor makes an attempt to check whether the critical section is under use or not, that is testing whether the lock is under locked condition or released condition. So that operation itself has to be an indivisible operation. So for that purpose, we always use some test and set instructions, and this can be implemented as a hardware lock mechanism also. And whenever the instruction is going to execute this test and set lock, it has to be executed in two memory cycles. Why? Because first it has to read the status of the memory, and only if it is not locked, the new process can acquire a lock by setting the value to 1. If it is already locked, it has to wait. So to do this, to check this operation, always it will consume two memory cycles. And note that the lock signal must be active during the execution of the test and set instruction. When a process is testing the status of the lock, at that time no other process should make an attempt to test. So this test operation has to be done only by one process, and it is going to be an atomic operation. So this is a key point which we have to observe in the inter-process communication and synchronization. And now, with respect to communication, as I mentioned earlier, we have talked about shared memory and no shared memory. If it is shared memory, we will call that as a tightly coupled system. And if it is not shared, it is going to be called as a loosely coupled system. If it is going to be tightly coupled, all the memory, the common memory is accessible to all the processes. So it acts as a message center, which is similar to a mailbox. One processor, if it wants to communicate with another processor, it will just type the message like a mailbox, like in the common memory, and the other process which is also sharing the same memory will be able to read the information. Coming to this loosely coupled, there is no concept of common memory, so obviously there is a need for passing the message from one processor to another processor. And with respect to synchronization, we have to ensure that mutual exclusive access is available, and by mutual exclusion we are able to protect the data, because at any point of time only one processor is allowed to update the data. If more than one processor makes an attempt to change the data, it is going to end up in a chaos. So that should not happen. So mutual exclusion has to be ensured. So this is one of the prime requirement for this inter-process synchronization, and usually this mutual exclusion is going to be implemented by means of semaphore. Already I have informed, semaphore is nothing but a binary variable which will always reveal the status of it. Is like a kind of a indicating the status of the lock. If it is 1, it will indicate that it is in use. If it is 0, it indicates it is free. And critical section is once it has begun, it has to complete the execution before another process access this region. And hardware lock, it is already discussed, so it is nothing but a mechanism which is available at the hardware level that can ensure this synchronization process effectively and efficiently. So the same thing we have discussed here, the communication, the shared memory, the loosely coupled system, tightly coupled system, I have informed. So various processor in a multiprocessor system must be provided with a communicating facility, and this communication is usually established by means of some input and output channel. So whenever the processor wants to communicate something, first it has to frame that message. So it has to structure the request, what is the message it is going to pass on, and by means of the procedure is it going to do, and always it will places this information in the mailbox with respect to the tightly coupled system. And the status bit will also be there, and the status bit is going to be a good indicator of whether a particular portion in the memory is in use or not, or free, relatively free. So the receiving processor can always check the mailbox periodically for any message meant for it, and if it is there, it will start consuming it. Okay, the more efficient procedure for sending the processor to alert the receiving processor is by means of an interrupt signal, because every time if a processor is keep on checking whether I have received any message from another processor, it is going to be a waste of time. For that option, the efficient mechanism could be that if a processor is going to receive a message, it can be interrupted by the sending processor. So upon receipt of the interrupt, the processor can just look into the mailbox and can make use of the messages. And again, if the shared resource is going to be accessed by multiple, obviously there will be a conflict. So to avoid this conflict, we have to assign the scheduling sequence. So who is going to access the resource? That order has to be priorly determined. And we have three organizations that have been used in the design of the operating system for with respect to multiprocessor. So one method is the master slave configuration, where one processor will act as a master and all the remaining will be the slave, and the master will have the control over the remaining processor. And then we can have separate operating system running in each processor, and they are going to be autonomous in nature, and they will be cooperating with each other to get the work done. And the third category will be the distributed operating system, where it will the resources will be distributed and it will be scheduled by the respective operating system. So in master slave mode, as I told, one will be the master and the other remaining will be the slave, and the master is going to decide everything. And in the separate operating system configuration, each processor can execute the operating system routines whatever it needs and get the work done. Whereas in the distributed operating system organization, the system routines are distributed among the processors, and however, each operating system function is assigned to only one processor at a time. It is also referred as a floating operating system. So this completes a discussion with respect to tightly coupled configuration. And coming to loosely coupled configuration, there is no common memory. So there is no possibility for passing the information through the memory. So for such cases, we have to frame the messages, and the messages have to be passed on from one processor to another processor. The communication is initiated by one processor and it is going to reach the other one, and how it is going to be informed is by means of synchronizing signals. The communication efficiency of the interprocessor communication system, it always depends on the routing protocol whatever we are going to use. It also depends on the processor speed, the data link speed, and the topology of the network. So all these factors will decide how this communication is going to happen in an effective manner. Coming to the synchronization part, as I told, we are going to make use of the semaphores, and multiprocessor system usually include many mechanisms for providing the synchronization, out of which the common popular method is going to be the binary semaphore. And apart from this binary semaphore, we also have the concept of counting semaphore, where it will keeps counting on the number of processors who are waiting for the resources. At any point of time, only one processor will be allowed to access the resource, and whoever has gained the control, that will be using the resource, and after its completion it will release the lock, and the token will be passed on to the other waiting processes in turn. The mutual exclusion with semaphore, it is necessary for the data to be protected, because if more than one processor makes an attempt to change it, then it is going to end up in a inconsistent value. So that should be ensured. So any mechanism which is going to be adopted for mutual exclusion has to ensure that the processor, only one processor will be allowed to change or allowed to update the resources available in the critical section. A critical section, already I think we have discussed about the critical section. So when the semaphore value is going to be equal to 0, the shared memory is available to any requesting processor. If the processor access the shared memory, it means that it is executing the critical section, and in that case it will set the semaphore to indicate that it is making use of that particular portion, and then it will release that settings after completion. Usually the other processor who is waiting for the resource will just check for the availability by means of testing and setting the semaphore value before entering and exiting the critical section. A hardware lock can also be provided, and this will generate a signal which will prevent other processor from using the system bus as long as the signal is active. And we also have the semaphores by means of test and set lock instruction. So there is an important hardware mechanism available, which is going to be referred as test to set lock, that is nothing but TSL. So what actually this instruction is going to do, if you just observe here, the test and set while locked operation will perform first testing of the status. To test the status, it has to read the memory variable m of sem, and after testing, if it seems to be 0, it means it is not in use. Then whoever wants to use that critical section will set that semaphore value to 1. So it will test for free, and if it is free, it will set it and then it will use it. So this is going to be an indivisible operation, and it is going to be done as an atomic operation. So this completes a discussion of the interprocessor synchronization, and the communication is going to happen only in case of the loosely coupled organization. In tightly coupled organization, the memory will take care of. Thank you.